So in the end, we have, because in this yeah, so let's see, in this consequence, which is that if you have a torsion-free Fuchsian group, then for every point in the hyperbolic plane, you have a group isomorphism between gamma and pi 1, and actually the point is that here gamma is actually the group of deck transformations. It coincides with the group of deck transformations of the cover from H to H modulo gamma. Right. So what is this theorem good for? Let's say. I mean, it's good for many things, but for one thing, it's good for is now. I mean, we saw examples, for instance, of certain Fuchsian groups with the property that when we considered the orbit space H modulo the action of gamma, it gave us a torus with 1 point removed, and actually somehow the geometric role of that point removed was that it really became a point at infinity. So in the end, the geometric picture we obtained was a puncture torus, but really with 1 point at infinity. And then you can ask the question. Okay, so now suppose I give you only the information of the genus, a desired genus, right? In the case of the torus, it would be 1. So a desired genus G, and a desired number of points at infinity, let's say S. And then one asks, is there actually some Fuchsian group gamma with the property that the quotient, that the orbit space is a closed surface of genus G with S points removed, but also in such a way that such S points play the role of points at infinity? Right? So it's kind of the converse question. Right? So for instance, for G equal 1, S equal 1, the answer is yes. We saw an example. Well, this theorem, this gives us one possible strategy to try and answer, because we know that if such a gamma exists, then automatically, well, torsion free, if such a gamma exists, then automatically gamma has to be isomorphic to this fundamental group of something that is computed only at the topological level, that is computed ignoring all geometric information, that takes into account only the topology. So given G and S, I can say, okay, form the compact surface of genus G. Well, form a compact surface of genus G, and then from that compact surface remove S points. Okay? Remove S points. So let's call the compact surface, let's call it sigma, right? And then these points, the S points, the subset with S points, let's call it M. Right? So M, it's the collection of the points that I removed, that I'm going to remove, so that the surface with the points, the surface with the points removed is actually sigma minus M. right? And then I know that if there really is going to be a gamma such that this is a surface of genus G with these S points at infinity, then gamma itself has to be isomorphic to the fundamental group of precisely this, with any point, any point you want. Let's say PT for point. Oops. Right. So what do I do? Well, when I'm asking, you see, now what I have is, here I have a group. What I want is to look for a discrete subgroup of PSL2R isomorphic to this. So the question of whether this information can be realized geometrically through a Fuchsian group amounts to asking whether PSL2R has some discrete subgroup isomorphic to this one. Okay, and then we have one criterion to know whether some set of we have a criterion to decide the following: given certain set of Mobius transformations, to decide whether the subgroup they generate is discrete, namely Poincaré's polygon theorem. So one uses Poincaré's polygon theorem to say, okay, it is always possible to realize this group. I mean, to find discrete subgroups of PSL2R isomorphic to this group. So you see, so you see so there are two steps. The question of whether this information can be realized geometrically amounts to asking about the subgroups of PSL2R isomorphic to this group, and to find, so to know that whether to know at least whether such subgroups of PSL2R exist, one can use Poincaré's polygon theorem to answer positively and say, okay, indeed there are Fuchsian groups that realize this geometric information. Yeah.
Maybe briefly.
So kind of what the point is that the point to the way one sees how the one uses Poincaré's polygon theorem, or if you want, the way one prepares the setup to this setup in order to be able to use Poincaré's polygon theorem in order to show that there indeed exists such discrete subgroups of PSL2R isomorphic to this, is the following. Before removing those points, you have the compact surface sigma, and there is a classical classification theorem of compact surfaces that says that just as pretty much the topological level, such surfaces can be constructed by considering certain 4G GONs, where G is the genus, and making some identifications, like similar to the one for the torus. Right, and then what one does is that one takes that description, and then instead of taking just combinatorial polygons, one says, okay, take now hyperbolic polygons, hyperbolic 4G GONs, right? and then do it, and then for instance, if when you remove the first point, that's the first vertex, that's the first set of 4G vertices, because they are going to be identified through the Mobius transformations, the side pairing transformations, and then you start adding to start adding the other points is kind of you start doing the kind of the cuts like I did when I introduced the second function, like the second point at infinity. And then this kind of then you set everything up so that you can say, okay, now I can apply Poincaré's polygon theorem, and then because of the way you engineer things, you know that the fundamental group of what you obtain is isomorphic to this. Sorry, that the Fuchsian group, that the Fuchsian group you obtain is really isomorphic to this one because of the way you engineer things. Yeah. Okay. And then so there always is, at least if you give me this information and you want the points this to be each point to be really realized as a single point at infinity. That can always be done. And then the next question is, okay, in how many essentially different ways can you do it? Right? I mean, if I have two such Fuchsian groups that give me the same combinatorial information, the same genus and the same number of points at infinity, well, on each of them, I can push the hyperbolic metric on H. I can push it here through P, because this is a covering map, so I can really push it. So I can obtain really a Riemannian metric here, and as being a Riemannian metric, you see, if I take two such groups, then I can ask, okay, it could be that they are not Riemannian isometric, right? That they are really not isometric. It's indeed the case that for many of them, one obtains things that are not really isometric, and then one asks, okay, how do I classify all possible ways of choosing gamma so that I obtain non-isometric things? So that's already kind of a moduli problem. Let me state it in a bit more in one more concrete situation. So maybe here. So draw the Poincaré disk, right? And then let's ask. So just as I asked, in this surface of genus G with S point removed, in how many different ways can I realize it via the hyperbolic plane and via a Fuchsian group? I can ask something similar, and actually it's a simpler question. A triangle, just a triangle which would be just given by just the information 3, right? In how many ways can I realize a triangle as an ideal hyperbolic triangle? So as a triangle, all of whose 3 vertices are points at infinity. Right? So for instance, this would be one realization. Essentially different, right? I know, for instance, that if I take this triangle and I apply a Riemannian isometry of the Poincaré disk, then the image of this triangle is going to be, in terms of hyperbolic geometry, essentially the same. Right? I can consider it essentially the same because it's just apply an isometry. So in terms of the space itself, which is the Poincaré disk, it's essentially the same. If you think about it, for any 2 triples of points for any 2 ordered triples of points in the unit circle, let's say this. So those two ordered triples, where I say, let's say that this is the first one, let's say the second one, let's say the third one, and I don't know, again the first one, second one, and third one for those two triples. Simple transitivity of Mobius transformations actually can be used to prove that there is exactly one Riemannian isometry of the Poincaré disk, taking the first one to the first one, the second one to the second one, and the third one to the third one. Which means the triangles determined by both of them, so by this one and then by the other one, are essentially the same. Yeah.
Is it immediately clear that so there's a
Yeah, I mean it's a valid question, but I would say one has to argue, but it's not so hard because uh, both of the triples lie on a unique circle in C bar,
right.
and that unique circle is the unit circle, and then because both of them were ordered in the same sense,
Yes, so that's
counterclockwise or clockwise, but in the same sense, the disk maps bijectively into itself, right? But yeah, it has to be argued, but it's not so hard. Yeah. But so the answer is that if I consider the problem of classifying all possible ways of imposing a hyperbolic metric or a hyperbolic geometry on a triangle in such a way that the vertices, which would be like the points are removed somehow, become points at infinity. It's essentially only one. Okay, and then I move to the case of the square. Let's say for the square, and again I'm going to work with ordered quadruples, right? And let's say ordered quadruples, and let's say ordered in the counterclockwise sense. Let's say I don't know 1, 2, 3, 4, right? So that I want to see all possible ordered ideal quadrilaterals, right? I mean ideal quadrilaterals with a distinguished first vertex. Okay. I mean not only as a set, not only as a subset of the Poincaré disk, but also kind of I want them given to me with a distinguished first vertex. Then I can say, okay, so up to simple transitivity of Mobius transformations on triples of points, I can always choose. I mean, there's always a Mobius transformation that sends the first 3 points of my ordered quadruple of ideal points to I, so that I is, let's say, the first vertex, minus 1, so that minus 1 is minus 1, so that minus 1 is the second vertex, and minus I, so that minus I is the third vertex. And what I know is that the Mobius transformations that did the job for my arbitrary quadruple of ideal points sent before somewhere, sends the fourth vertex somewhere. But I cannot say that I can send it at will here, because the simple transitivity, right? So that means that for instance this quadrilateral that is determined here, for sure, is not going to be isometric to the one, let's say here, when I take I. At least not with a, with an isometry. That sends the first distinguished vertex to the first distinguished vertex. And so somehow my conclusion is that somehow it seems that the space of ideal quadrilaterals in which a first vertex is distinguished is parameterized by this open interval, by the open half circle. Right? So it seems that it becomes a decent topological space. You see, kind of home. I would say I would want it to I actually want to say, okay, it's homeomorphic or even diffeomorphic if possible to just an interval. And then in order to do that is that one needs to really formalize what is the concept of moduli space. Now you see here is kind of the point, the starting point is that one wants to classify certain type of objects. That's somehow the starting point. But formally, one really needs some notions from category theory. And then, as far as I know, you have not seen yet that, right? So let's see how far I get. And then at most I'm going to reach the point at most, kind of just before being able to really discuss this. So it's really going to be an incomplete lecture, but okay. But so let's talk a little bit about categories, which in any case is kind of really just the standard concepts from category theory. So okay, so this looks a bit maybe intimidating, but it's actually not so hard. In a category C, there are objects and there are morphisms between the objects. Okay, so for objects X and Y, there always is a set of morphisms from X to Y, denoted hom C. That I'm going to denote them hom C from X to Y. Okay, and there's a rule, and there's a there's a composition rule. So you see, given any three objects, if then the morphisms, any morphism from X to Y, and it can be composed with any morphisms from Y to Z, so that in order to obtain morphisms from X to Z, kind of similar to what happens when X, Y, and Z are, for instance, sets, and I take a function from X to Y and a function from Y to Z. There's a composition that produces a function from X to Z. Or for instance, when X and Y are groups, and Y and Z are groups, and when X, Y, and Z are groups, and I take a group homomorphism from X to Y and a group homomorphism from Y to Z, I can compose them, and the result is a group homomorphism from X to Z. Okay, and each object carries its own identity homomorphism. So to be an identity homomorphism means that that the identity composed with anything is the anything, right? I mean, whenever it can be composed, whenever the composition makes sense. And one requires that, just as in the case of composition of functions, composition of group homomorphisms, composition of ring homomorphisms, etc., that the composition is associative. Okay, so one has a class of objects, and one has a class of morphisms between the objects. Morphisms can be composed. Composition is associative, and there are identities. Okay, think, for instance, about just the category of sets. That's kind of the first category one encounters ever. The objects are sets. The morphisms are functions between sets. This one is the set of all functions from set x to set y. Composition is just the composition of functions. Right? So given a function here from x to y and a function here from y to z, I can compose and obtain a function from x to y, and there's an identity function for every set. And composition of functions is associative. Right? So the point is that this sort of basic structure appears quite frequently. So there are many examples.
May I ask
yes.
question?
Yes.
So there seems to be a difference.
No. For instance, the universe of all sets. Let me call it like this. U. The universe of all sets is the disjoint union of all sets of all sets of this type. And it's not a set. Right? Right.
Okay. Okay, and then you just say it's a class. So
yeah. Yes. Sorry. Maybe that's so. So are you well acquainted with this Russell paradox?
To some extent, but I guess the point which I've
yeah.
What a class then.
Right. Okay. Yeah. So yeah, I don't want to enter into discussing that because that would take me some time. I mean, but let's say here the point is that okay, these are kind of these are small in the sense that each of them is a set, but here the number of things you see, the number of such things that you are that we are taking union is so big that the whole content is just too big. That's the thing. And so this may fail to be a set. So you see, it's kind of each of these is kind of a small bag, but it can be that it's many bags that you are taking all together. So that this whole thing doesn't fit into a bag. And that's what may happen.
But is there like a formal definition of what a class?
No.
Okay.
But if you think about it, there's also not a formal definition of what a set is. I mean, yeah, because then it's whatever definition you give me of what a set is a collection of things. Okay, what is a collection?
Okay.
Yeah, and then you start going.
Okay.
Yeah, so something similar happens to classes.
That's exactly the point where the paradox comes in.
Right.
You can say, well, this should be a set because the usual definition or the intuitive definition of set would allow me to consider this a set, and then you get a paradox. Right?
Mm-hmm.
You realize actually.
Okay. Yeah.
Okay.
Yeah, we can discuss some other time if you want. Yes. Yeah. Yeah, and so somehow for me, class is by saying class, I'm just allowing this to be so big that may fail to be a set.
Okay.
Yeah. Yeah, and then there are many examples of categories. One is the category of sets. It's kind of the first one encounters ever. The category of groups. The objects are all groups, and the morphisms are group homomorphisms with composition as defined as the one you know, which is actually comes from composition of functions. Okay, the category of abelian groups. So the objects are abelian groups. Morphisms are just group homomorphisms between abelian groups. The category of topological spaces. So there the objects are topological spaces. The morphisms are continuous functions. The category of Riemann surfaces, whose objects would be all Riemann surfaces, and the morphisms would be holomorphic functions between Riemann surfaces. This one, the category of from linear algebra, right? So the category of finite dimensional vector spaces. Let's say over the complex numbers, kind of just to fix ideas over, but of course over any given field, there is one such category. Objects are vector spaces. Morphisms are linear transformations. Well, here vector spaces of finite dimension. So okay. This one, the category of pointed topological spaces. So objects are pairs, right, consisting of topological space and some certain point in the topological space. And the morphisms are continuous functions that preserve the base point, that send base point to base point to base point. So for instance, given here two such objects, a continuous function from x to y that fails to send x naught to y naught would not be a morphism from this pair to this pair. At least not in this category. Maybe in this one, but not in this one. So they are different categories. And the fundamental groupoid of a topological space. So here the objects are the points of the space, and the morphisms from one point to another are the homotopy classes relative to endpoints of curves going from one point to the other. Okay. Now, so somehow the notion of category, what it does is somehow one wants to study not only the objects, but kind of the objects and how they are related via their morphisms. And then, of course, comes the idea that, okay, but then maybe I can compare two categories. Right? Like when we introduce the notion of groups and say, okay, maybe I can compare two groups. Right? And then there's the notion of group homomorphism. Maybe I can compare whatever two things, right? There's always this kind of immediate idea, right? That compare two of them. And the way to compare them, there are two possible ways to compare two categories: the covariant way and the contravariant way. Let me explain the covariant way. So a covariant functor. So what can it be? You see how can I compare to categories? What comes to my mind? Well, maybe I have one way to go from the objects of one to the objects of the other, and from the morphisms of one to the morphisms of the other, in such a way that I can just go through, go from one to the other. What would it mean? Well, you see, from to each object of C, I would assign an object of D. To each morphism in C, I would assign a morphism in D. Well, the first thing I would like is that it is kind of that F behaves as somehow taking the shadow of these morphisms. So in the sense that for any two objects in C, if I take a morphism in C from X to Y, the associated morphism goes from F of X to F of Y. Right? So that kind of I go from C to D, and then for these two objects and a morphism, this morphism really goes kind of in a coherent way there. But not only that, I mean, in a coherent way in the sense that it somehow it starts not arbitrarily, but it starts where somehow it should start. This one starts where it should start and ends where it should end. Right? So somehow that really somehow capital F really I wanted to really map somehow the structure of C to the structure of D somehow. Okay, once I asked for this, what else? What are the other ingredients of the structure of C? Well, its composition and the identity morphism. So I just ask F to respect that, to send identity to identity, and composite and so that I can compose before sending or after sending. Right? So that somehow really capital F gives me a way of passing from the structure of C to the structure of D. Right? And of course, F, you see, some information of C can be collapsed along the way, so that somehow the image of F may through F I may lose some information, and in D there may be some extra information not seen by F. Okay. Okay. Anyway, I mean, if what I just said is too much, forget about it. Okay, now that's the covariant. That's the covariant way of comparing two categories. There's also a contravariant way, because you see, it may happen that you just reverse arrows. For instance, take the duality of vector spaces. Right? I mean, if I have a linear map from a vector space V to a vector space W, and I consider the dual vector spaces, what F induces is a linear map, but in the other direction, right? I mean, namely, given phi here, it really goes to F followed by phi, right? So somehow duality, it's really kind of going to vector spaces and linear maps, associates vector spaces and linear maps, but it doesn't do it this way. It reverses direction. So we allow that, and then we just say, okay, that's the contravariant way. But the idea is the same. To objects of C, I assign objects in D. To morphisms in C, I assign morphisms in D. But now I require that when I take a morphism, somehow its shadow somehow points the other way, points kind of opposite to the original. And then that's the one. Once I require that, then the rest is just okay. So just make it reflect the, not reflect, but make it preserve the structure of C. So composition goes to composition, but of course now here, for instance, this one, you see, if F goes from X to Y and G goes from Y to Z, then of course then this one goes from F of Z to F of X, and I also have F of Z, F of G, F of Y, F of X, F of F. So you see, it's kind of, I still have some kind of coherence, in the sense that when I apply this, or I send and then compose, at least I know that both start and end in the same place, and then I just require that they be equal, and identities to identities. Right. So somehow what it does is it still maps the structure of C to the structure of D, but morph wisely, it just reverses. Right? So it's like as if D contains some like opposite some certain information which is opposite to the one in C. If you think about it, that's just because how we write arrows. If we decided suddenly to write arrows the other way, it would really be kind of the same. anyway, anyway, I don't want to go much into that. So examples of first of a covariant functor, which is a fundamental group. So to each pointed space, I associate the fundamental group, and to each morphism, well, we saw that I can go from the fundamental group here to the fundamental group here, if I have a morphism, right? I mean, of pointed spaces, so that f maps x naught to y naught, right? And the idea is very simple. Given a curve in x, I can follow that curve with my continuous function and obtain a curve in y. And then if the curve is a loop based at x naught, then the image is going to be a loop. And if f sends x naught to y naught, then the image of the curve is a loop based at y naught. So it's kind of, but you see, but the basic idea to produce this one is very simple. If I have a curve in x, that curve, if I follow it by a continuous function f, small f, well, I just obtain a curve in the codomain of the function. So, well, and this is actually a covariant functor from the category of pointed topological spaces to the category of groups. And duality is an example of a contravariant functor. Okay, so vector space duality. Right, so, and this is easy. And then here recall that I'm restricting to just finite dimensional. So it's a contravariant functor then from where to where? From finite dimensional to finite dimensional. The dual of a finite dimensional vector space is finite dimensional. And then just notice, so this is covariant. So at the level of morphism, the direction of a morphism gets reversed when I apply duality. But if I apply duality again, it gets in the same direction. So it's kind of double duality is a covariant functor. Actually, composition of two contravariant is covariant because it kind of, the first one reverses the direction of morphisms and the second one reverses them, so it's kind of corrects it corrects it. Okay, so we have a way of comparing two categories. That's the notion of functor, either covariant or contravariant. Somehow I think they really seem almost like kind of almost the same notion, but somehow I think the contravariant notion is more natural. That of course is only an opinion, right? But yeah, two more. So two more examples of functors. Let me just mention just the contravariant version, and this is kind of it's one of the most important examples of functors. So, which is, if I have a category and I fix an object, I can form. I can consider, you see, I'm fixing my object, and then I can consider all possible morphisms from all possible objects in C to my fixed object, and that is a functor. Now, what does it mean really in detailed terms, for informal terms? Well, that to each object we associate the set of all morphisms from X to Z. Right? I mean, so X is going to be sent by the functor to hom XZ. And if now I have a morphism from X to Y, well, now I want and now I want a function from x, y, z to from home y, z to home x, z. And what I can do is, somewhere is my object z is somewhere there, right? And given my morphism from x to y, what I do is, to each morphism from y to z, I associate this composition. That's what I do. So to each g, I associate this one. Okay, why? Because you see, to each object, I want to associate a set. I know which one. And now to each morphism, I want to associate a function. Because I want a functor from C to Z. So to each object, there has to correspond an object here, namely a set. It's this set. And to each morphism, there has to correspond a morphism here, namely a function. A function between what? Between whatever I associated to the domain of the function of the morphism, and whatever I associated to the codomain of the morphism. Yeah, or is it yeah? So somehow this f is the f here, to which I want to associate a function here. From where to where? From this guy, which is what I associated to the object y, to this guy, which is what I associated to the object x. And how can I do it? It works as duality. You see, now this is the one that is fixed here. I want to define a function, and then given something here, namely given this g, what can I associate to g using f? Well, I can just compose, and that's it. And this is a contravariant functor, and it's the so-called contravariant home. Somehow, in the end, the idea is that somehow one wants to encode the information of any given object of C into all the possible morphisms to Z. And this is an idea, and this is an idea like which kind of exploited to its maximum in algebraic geometry. Like when one speaks about schemes, these functors are like super important there. Okay, and now then you would say, okay, so now ready, right? Like we can breathe, and then no, not yet, because now we want the point is that, you see, there in a category there is the notion of isomorphism, right? I mean, for instance, in the category of groups, we have the notion of isomorphism. What is an isomorphism of groups? Is a morphism of groups which has an inverse in the category of groups, which has an inverse which is a morphism of groups, and it's a two-sided inverse. So if you think about it, that notion can be given for any category. So I can talk about isomorphism in any given category. And then it could be that that maybe I have two functors between two categories, and that one of them is the other one but disguised, in the sense that it could be that I have two functors. You see, I have my category C, my category D. Maybe I have two functors, but then maybe they have almost the same behavior, in the sense that if I take any object in C and I look at the corresponding images in D, that they are isomorphic. And it could be that maybe the functors are almost the same, except that instead of sending an object to exactly the same object, it's being each object is being sent to isomorphic objects.
What does isomorphic mean in this context?
So in a category, each object has its own identity. So I say that two objects in a category are isomorphic in the category if there is a morphism from one to the other that has an inverse in the category, right? What does it mean to be an inverse? That both compositions are the corresponding identities of the objects in the category.
And in the set of morphisms, there only has to be one that satisfies that. It doesn't have to be the entire set of morphisms.
Right. It's enough with one. Okay. Yeah. There could be many isomorphisms. There could be that for some pair of objects, many. You see, when I consider all the homomorphisms from one to the other, that a good chunk of them are isomorphisms, but another good chunk of them are not isomorphisms. Yes, that's perfectly possible. Yeah. But so you see, it could be that two functors really have the same behavior, except that one of them is giving me objects, not the exact same objects as the other, but isomorphic ones. And then I would say, okay, and that they really are the same functor but disguised. If when I send with both functors, when I send with both functors, then I can pass from these images to the other images simultaneously. And that's the notion of natural transformation. So the notion of natural transformation allows me to compare to see when I can pass from one functor to another, because it may be that sometimes one is another functor in disguise. Suppose now that I have two categories and two functors, and let's say contravariant. And a natural transformation from F to G, you see, is a collection of morphisms in D, which is what I just said, that somehow after passing through with both functors, this collection somehow allows me to go from the images with respect to one functor to the images with respect to the other functor simultaneously. But what does it really mean simultaneously? Well, that if you give me any morphism in C, and I consider the image of this morphism with respect to the two functors, and remember they are contravariant, so the images of this guy under F and G go in the opposite directions. So go from y to x, well, from f of y to f of x, and from g of y to g of x. And this simultaneous passage, this notion of simultaneity is really the requirement that this diagram commutes. That this composition is the same as this composition. So that you see somehow the idea is that considering this morphism, or mapping and considering this morphism, somehow is the same. That somehow this morphism is some sort of image, some sort of shadow of this morphism. So this one. Yes? So.
But now we need it for every morphism.
Yeah, for every morphism. Yeah. Because you see, F this F maps the whole structure of C into D, and G the same, and then somehow we want that eta maps the whole behavior of F to G. Somehow that's somehow the idea, that considering the whole behavior of F is mapped into G, into the behavior of G. Okay, and then an isomorphism, F eta is an isomorphism of functors if all of these are invertible. I would prefer to say if there is a natural transformation in the opposite direction such that the compositions are the identity functors or whatever, right? But that is kind of, it's starting to become a bit kind of too much information, right? But I would just leave it like this. And this is, and then you see that two functors be isomorphic. That's somehow the notion that two functors are the same, are essentially the same, except that one may be the other in disguise. And somehow eta is kind of putting the disguise everywhere, you know, like disguising every object somehow simultaneously.
Yes. So are we considering categories now as a category?
I'm not going to go there. Right, I'm not going to go there. But this looks like a morphism between.
Yeah. Right. So
yeah. Yeah.
Cyclical.
Right. Yeah. I'm going to stop there because otherwise I do run into logical problems. Yes. Yeah. Because then I would say you see that the whatever of all categories is a category, and then I run into the same paradox. So I'm
cannot be classes made out of classes.
Yeah. So I'm really just going to stop there. Yeah. But that's all I need. That's all I need to, in half an hour, describe what is a moduli problem. Just by the way, so for instance, the point is the double duality. Well, it's a covariant functor, and I gave this for contravariant, but then see you can give the corresponding notion for covariant functors, and the double duality functor is an isomorphism between the identity functor. Sorry. The double duality functor is isomorphic to the identity functor of the category of finite dimensional vector spaces. In other words, if I take a finite dimensional vector space V, it's double dual. It's the original space but in disguise. You see, naturally isomorphic. Exactly. Yeah. Where the passage, the natural transformation from the identity functor to the double duality is to each vector in V corresponds to evaluate in V. So somehow that's the point. Somehow in the end the point is that each vector in V is determined by what it does to all possible linear functions, to how all possible linear functions from V to C evaluate in the vector. No, so, okay. I mean, here you can see in the notes like all the details work. Okay, and now what is a moduli problem? Right? And then this is really, I'm not an expert on moduli spaces or moduli problems. Here I would recommend you to have a look at a very nice set of notes by David Benz-V, just called moduli problems, moduli spaces, sorry. I mean, you can just go to the course website, and then you're going to see the reference. And yeah, there's some other harder to read, but also very nice notes by Kai Berendt. It's called Introduction to Algebraic Stacks. That's a lot harder to read. And then there is a book by Newstead, I think it is. I think it's by Newstead, called Introduction to Modular Problems. And orbit spaces. And its first chapter is it's very nice. Anyway, so somehow you see we already encountered somehow moduli problem. So a moduli problem is a classification problem, and usually one starts with some class of mathematical objects in which there is an equivalence relation, like we did in, for instance, in the case of the ideal triangles, right? There was like the ideal triangles, but modulo the relation of that two of them would be equivalent if there is an isometry that takes one to the other, right? A notion of family of objects, and how it's like a family of objects of that class over an arbitrary, let's say, topological space. This we didn't really see. We didn't really see the definition of what would be a family of ideal triangles over a topological space. That we didn't really see. Here in this one, there are some really nice examples. So in this introduction to algebraic stacks, of that sort, not of ideal triangles, but of that sort, of what is a family of like triangles, of Euclidean triangles, and so on. So I really recommend that you try to have a look at this, although it's hard. It's, at least for me, not easy to read. And together with the notion of family of objects over a topological space, which somehow the picture one somehow many times draws, is that a family is like one draws the topological space, right? And somehow the family is drawn like lying above X somehow. And then you see with each somehow like this one draws them as if it was fibering over X, where each of these is a member of the class C. Somehow that's kind of the picture one draws for a family. And then there's also a notion of equivalence of families, because it could be also that you see that one has two families, but one family is pretty much the same as the other one, but in disguise. So there's always this type of situation. So one has to always take that into account. Okay, and now often my class C is actually the class of objects of some category. Like for instance, if you ever see the moduli space of Riemann surfaces, somehow then one considers the moduli space of Riemann surfaces of genus G. then one is taking the category, C would be the category of all Riemann surfaces of that genus. Where the morphisms are holomorphic, holomorphic functions. Okay, and this equivalence relation is usually in those situations is the notion of isomorphism in the category. Okay, and then one wants to classify the objects in C modulo this equivalence relation. And then you can say, and then many times you can say, okay, just take that, right? I mean, just take the partition, right? But the point is that one wants to give some geometric sense to that, or some geometric structure to that somehow reflects all the possible ways that one can form families with those objects over spaces. Okay, so one usually looks for a moduli space, so some space M. I mean, let's say some topological space, let's say, whose points parameterize these equivalence classes bijectively, but in a meaningful manner, so in a somehow geometric meaningful manner. And by this I mean that somehow the topology of this space ends up reflecting all possible ways of forming such families. Okay, so I mean, yeah, I know that this is this may be not so easy to digest. Now, let T the category, let's say of topological spaces. Right. So somehow it's T this T is the category of spaces over which I'm going to form the families. Okay, so I'm going to assume that I am given my class of objects that I want to classify, right, and that I'm given the equivalence relation. I'm going to assume that I have been given some notion of family of family of objects over any given topological space, and that I am given a notion of equivalence of families. That I'm going to assume. And then T is the category of all spaces over which I'm going to be forming families. Okay, now in order to really have a hope of finding such space M, somehow the moduli problem has to be well posed in the sense that one has to be able to produce from the notion of family and equivalence of families, one has to be able to produce a covariant functor. One has to be able to produce the functor of families as a covariant functor. In the sense that given any family, you see here this would be like my X here in the previous picture, and E would be kind of this thing that I draw as if it were kind of fibering over X, etc. I mean, here I would have to draw it with some shape like this, right? But okay. And one has to, like, the first thing one asks for is that given any such family and any continuous function into X, one should be able to pull back the family along the function and obtain a family here. So there has to be some notion of pullback. Yeah, okay, so maybe okay, so this is This is the last lecture. Okay, so this notion of pullback somehow is reminiscent of the notion of pullback of just from topology. If you have just two continuous functions, let's say y to x like this psi, and then let's say from some other set, let's say this phi, there always is a pullback. So there is some space here. I don't know. Let me call it omega, just for lack of creativity. And so that somehow one way to think about this is that somehow it pulls back the fibers of phi, in the sense that if you take a point here and you map it and you look at the fiber here, that fiber is pulled back here. Okay, I don't have much time, but otherwise I would stop and really explain this in detail, because there are like very beautiful pictures that one can draw. But anyway, so somehow this notion of pullback that one requires to exist is reminiscent of the notion of pullback in the category of topological spaces. And then that's something one requires, that families can be pulled back, but kind of in a coherent way, so that equivalent families really are pulled back to equivalent families, so that one can really form a functor saying, okay, to each space X, I associate the set of all equivalence classes of families over it, and then to each function, I have an associated, to each continuous function, I have an associated function in the opposite direction that maps an equivalence class of families here to the corresponding equivalence class of families here. And then that way form a contravariant functor from the category of topological spaces over which I'm considering families to this one. Okay. And when that can be done, somehow one thinks that the moduli problem is well posed, in the sense that at least you can express your classification problem as the existence of certain functor, in terms of a certain functor, that families form a functor, that your notion of family forms a functor. And then we come to the concept of fine moduli space. And well, first, you see, we saw the functor, the contravariant hom, right? Given this one, right? Given a category and an object in the category, I can form the functor hom blank to Z, which takes into account all the possible morphisms in C that go into Z. Okay, we know the notion of isomorphism of functors, which tells me that two functors are isomorphic is kind of if one is the other one in disguise. So in some situations, there could be some functors that are some hom blank Z in disguise. Such functors are called representable. So a functor, a contravariant functor, is representable if there is some object in the category, and here it should be the category T, not C. Sorry, here it should be T. Yeah. if there is an object such that the given functor is really this contravariant home in disguise. Right? So that it's isomorphic to that functor through some natural transformation. Okay, and now suppose I have a well-posed moduli problem as before, so that I have some classification problem in which I have some notion of family and some notion of equivalence of families, and that it in such a way that there is the notion of pullback of family that allows me to um, um, express my classification problem as a contravariant functor, right? And then we say that the moduli problem has a fine moduli space, let's say m eta, if the functor of families is representable, and it's representable by m with this natural transformation. That somehow you see this natural transformation somehow takes off the disguise somehow. Okay, so that's a fine moduli space. It's just a solution to it's a kind of an object that represents functor of families. Okay, so it's less than 10 minutes. So now suppose I have my well-posed moduli problem, and that there's actually a fine moduli space. There may be none, because it is indeed the case that there are some functors that are not representable. So it's perfectly possible that a moduli problem is well posed but doesn't admit a fine moduli space. And actually, with some practice in categories, it's easy to produce. So such things are easy to produce. Okay, but suppose that there is a fine moduli space. So and take any topological space, right? So remember that here T is the category of spaces, and that I'm considering that I'm forming families of objects of C over those spaces. Okay, and now you see, since I'm assuming that this is a fine moduli space, I have this passage from phi to this other functor, which in the end, if you recall the notion of natural transformation, which is here, this eta really is for each x I have a morphism, because it's a simultaneous passage from one functor to the other. So this phi is this eta is a simultaneous passage from this capital Phi to this. So for each x, I have this morphism, a morphism where in the codomain of the functors, but the codomain of these functors is the category of sets. So this is just a function. And now you see this function, what it tells me is every time you have a family over x, you automatically have this eta associates to that family a continuous function from x to m. And then the fact that eta is an isomorphism of functors means that all of these are invertible, which means that this is a bijection. So what I'm in the end obtaining is that there is a bijection between equivalence classes of families over X and continuous functions into M. So you see my space M encodes the notion of families by precisely all the continuous functions into it. That's how it encodes geometrically the families into the families over X. So you see, constructing families over X becomes finding continuous functions to M.
I'm sorry, what was M again?
M is a fine moduli space for this, and by fine moduli space, what I mean is a space that represents the covariant functor of families, so that eta is a natural transformation from the functor of families to this contravariant home. So M is this space, right? And eta goes from the functor. It's a natural transformation that goes from the functor of families to the functor home blank M. So it transforms the functor of families into this functor home. Okay, I know it's hard. It's not easy to digest in just 1 hour or less than 1 hour, but I'm about to finish. So you see, this already tells me families over X are encoded precisely as continuous functions into M. So somehow the fact that your moduli problem was well posed and admitted a fine moduli space allows you to reduce the problem of finding all possible families over any given space X to simply describing the continuous functions from X to M. And the next thing that it says here is that actually, does it say it there? No, it doesn't say it here. It says in the next. So because now consider just, you see, the space with just one point, this topological space with just one point. Okay, then f of it is equivalence classes of families over one point. So it's all possible families. Sorry, all possible families that are equivalence classes that I can form. Equivalence classes of families that I can form over one point. If you think about it, is just the objects in C up to equivalence, because for each such object, for each such object, I just put it as a family over a point. Okay. Anyways, so
is C now the category of all spaces
that I want to classify. No. What I'm no. This is the space with only one point.
Yeah.
This is still the class of objects I want to classify, and this is the equivalence relation that I gave to it. So somehow, if you want, this is the category, let's say, of ideal quadrilaterals, as I did before. Modulo the equivalence relation that two of them are equivalent if there is an isometry between them. And then it is hidden in what I said and in what I have not said, that the equivalence classes of families over a point are in bijection with the equivalence classes of the objects I want to classify. And the intuitive idea is that if you give me an object in C, I just consider that object as a family over a point. That's kind of just the intuition. And that the equivalence of families, in that case, gives me precisely that if I have two objects in C, and I consider them as families over one point, the families are equivalent as families precisely if the objects are equivalent under this. Yeah, I mean, that ends up happening. My point is that then I have this function that goes from here to M, and it's a bijection. It's a bijection between this guy and this guy. I mean, the continuous functions from this one point space to M is canonically M. Right? I mean, for each such function, it just picks a point in M. Right? Picking a point in M is just the same as. Okay. And then what ends up happening is then that since this is a bijection, what I see is that M really parameterizes these equivalence classes bijectively. And the rest, when I'm run out of time, the rest is that actually one can find a special family over M, in the sense, a special family that has the property that with respect to what we saw here, that every family over an arbitrary space corresponds to a continuous function. Well, it ends up happening that if you give me a family and you consider the corresponding function, then this special family over M, when you pull it back to X, is precisely the family that you gave me before. So, but I ran out of time. So this is the end of the course. Now the thing is, what the kind of the next step would be to really formulate the problem of, let's say, classifying the quadrilaterals, the ideal quadrilaterals, as a moduli problem. So I would have to give you what is the notion of family over an arbitrary space. Right? So I would have to tell you the definition of what is a family of ideal quadrilaterals over a space, and the mental image would be that you have your space, and somehow it would have, and then a family over that space would be a kind of a bigger space, and some function, so that the fibers are ideal quadrilaterals. So somehow that's the mental image that one gets. And then I would have to see that to really verify that these notions really fit into this machinery of contravariant functors, and see that this half circle, this open interval in the half circle that we saw, really occurs as a fine moduli space for that. And then the next thing, when things really start becoming interesting, is when instead of quadrilaterals or so on, one thinks about Riemann surfaces, or if you want, hyperbolic surfaces, where one says, okay, now I want to find the moduli space of all Riemann surfaces or hyperbolic surfaces, if you want, of a given genus and a certain number S of points at infinity. So I would have to formulate a moduli problem. So in particular, I would have to tell you, I would have to define for you the notion of family of such surfaces over a space, and somehow the mental image is that I would have a space, and then a family would be like some bigger space with a continuous function, so that each fiber is one of these surfaces. Right, and then one starts speaking about moduli spaces. I mean, kind of Riemann surfaces. Okay, but that's it. So